Last segment we discussed about two things primarily. First one was about another interpretation or another viewpoint, how to look or how to visualize the reaction from the ground when friction is involved. And the second point was the topics basically which we will be discussing, and to be specific, how wedge are important or why wedges are important, and how wedges can be understood to understand screw threads properly. Okay, and as promised, this segment is about the wedges. Okay, now to make the thing simple and formal, let's have a system like this. Say we have again a wedge. Okay, so this is our canonical form when we say a wedge structure. Okay, and this is on ground. Okay, so these are straight lines. So please assume that they are straight lines and there is no gap between them. Okay, and this is the wedge, which we will consider to be massless to make things simple. Okay, because with respect to the mass which we are trying to lift off using this wedge, as compared to that, this mass is negligible, and that is why we can assume that it is negligible. And then over that we have, say, a block of mass m. Let me not write here, say mass m, not even here because I want to do something. Okay, say mass m. Okay, and then we have also got some stoppers so that this mass will not fall off. Okay, and we put some rulers over here. It's a representative thing to tell that there is no friction involved in this. It's almost like free to move, as in when we apply a force from this side. Okay, so when we apply a force F, this mass will be lifted up. Now to analyze that, we should draw again, as we have been doing, that we should draw the free body diagram. This is like a multiple connected bodies. Okay, so let's try to draw the free body diagram. Let's first draw the mass m, which is on the top. So now say suppose this is the thing, and let me draw here the angle alpha. Okay, so this is angle alpha. Okay, now if this is the free body, so from where all the forces will come, let's see. One force is coming from the gravity, that is m times g. Then another force which will come from say the wall, and because it's frictionless, so the force that will come from that side is perpendicular to this. Now at this point, sometimes students get confused that should I show it on only on one side. For example, suppose this I call R. Okay, there are in the picture I have taken this as R3 because R1 and R2 I'll just draw. Now the confusion which I was talking about is this. Now should I show reaction only on this side or both side or on this side? The thing is, we will show this only on one side, okay, not on both sides, because the reason is when we try to push this side or the whatever we do, or the thing is coming down because we have removed the force or something, the body will be touched to one side of the wall only. it will not be touching both the sides. Okay, it's not in a what do you call that, press fit kind of situation. There is a slight play, there is a slight gap between the walls so that it is smoothly moving, and at any point of time only one side is giving a support. Okay, the other side support is mean the reaction is zero basically. Okay, and now on the point of whether this side or that side, this force again is transmissible, so there is no you can show it here also and then here also, there is no issue. Okay, then comes another force will be coming, which will be a reaction from this wedge. Okay, now that will be, say, I'll first draw the perpendicular here. Okay, and that reaction force I would like to draw at I'll pick some other color, maybe say this, like this. Say I'm calling this R2, yeah, and this is say 90 degree. This is the normal to that surface. So here I want to make it that point clear that instead of showing it normal reaction and the frictional force, I am showing it as the complete reaction. So this is the alternative view which I was talking about in the previous segment, which you now should get into the habit of, because see, the reason is, if you show it as component form, you will think that it's a force body, but if you show it like that, then basically you can say that it's a 3-force member, and you know some good properties of 3-force member, and so that can be used. Okay, but and then at the same time we are not losing any information while we draw that. And if things are just on the verge of slipping, okay, then this angle will be phi, right? The angle at which the angle of repose, you can say the angle that the normal, not the normal, the reaction, the maximum angle which the reaction was making with the normal. Okay, so that is that angle phi. So that means this R2 will start from here, it can rotate like that, but it will stop here. It cannot move or rotate beyond this. So that's the limit. This phi is the limit for that R2. Now these are the three forces which will be shown on the free body diagram. Then what about the wedge? Suppose I try to draw for the wedge. Let me draw here. I think I won't have space here. So let me draw here. Okay, this is to, okay. Now if that is so, then if this is the reaction force, it was coming from the wedge onto the mass, so exactly the opposite, equivalent opposite reaction will be acting on that. And if I draw the perpendicular now to this surface, this is bad drawing, I think. This is even worse. Okay, let me settle with that. Now if that is the perpendicular to the surface, then I can in fact draw the actual perpendicular to the ground like that, say y axis like that, just for to make it clear that this is perpendicular to this surface and this is perpendicular to the ground. So that means this angle is anyway, this angle will be alpha, and this one will be just exactly in this direction, right? So this is R2. I'm writing the magnitude of the force, and so exactly now if this wedge is pushing the block upward, that block will be pushing the wedge downwards. So that's what has been pointed out here. And yeah, and then this angle should be equal to phi, right? This is phi and this is phi, because again in this way the reaction force maximum could come up to here and it stays there because it's on the verge of slipping now. And what else are acting? So from that side a force P, F, okay, F, and then there will be a force from the ground, okay. Now from the ground there will be a force which will be, say, suppose this is your perpendicular to the surface which is in line of this, and then there will be a reaction force which will be like this. This I call, say, R1. So R1, R2, R3. So these are the three reaction forces, and again, yeah, here if everything is on the verge of slippage, so this is phi. Okay, so this is basically the free body diagrams of both the wedge and the block. And the point which I was trying to make, that these are three force members. So what is, and then suppose they are on the verge of slipping, means they are in equilibrium. What it means is, if you try to draw these vectors, tip to tip, then they will pass through the same point. They have to pass through the same point. That means, so suppose mg is acting like that, and say R2 is acting like that. So then R3 must pass through that. So this is R2 and this is R3. So they must pass through the same point. Okay. So that means, and then it is sure, for sure the mg thing has to pass through the center of mass. So that means both these forces also have to pass through a line which is perpendicular, passing through the center of mass by default, because this is mg, this is mg, okay, and R2 and R3. And then if we draw them tail to tip, okay, so then how it should happen? Suppose I draw them tail to tip, then R3 should be something like that, then mg should be downwards. So we are drawing tail to tip, okay, so this is mg, and then R2 should be in this direction, so as to just match this tail here. This must be R2. Is that fine? Yep. And yeah, and this angle being equal to alpha plus phi, because you see here, if I draw the actual vertical to the ground through which mg passes, so this is alpha. So this angle is alpha plus phi, and this is the vector diagram. So from this graphically you can actually evaluate what happens when everything is just about to move into set into motion. Now coming here, again the same thing. Okay, so now let me draw here. So if I draw R2, it should be like this, say R2, and F is in this direction. So F is in this direction, and then R1 should be such that it will just join that thing or complete the triangle R1. And if I draw, say, the vertical here like that, this is phi, and so this is alpha, right? Is it or the full thing with respect to R2, how much it should be? let's see, R2 and R1. So, R2 and R1, now this is making alpha plus phi with the vertical. That means this angle R2 with the vertical is alpha plus phi. Alpha plus phi. Is it so? Yeah. Is that fine? So these are the things, and then again similarly here, these three things, if these three forces, if we draw them tip to tip, they all will have to pass through the same point, because it's a three force member which is in equilibrium. Okay, now so that is about the free body diagram of the wedges, but then there is a beautiful concept which is involved in this. So this will tell you, if you solve these equations now, that means either you solve it by graphical means or by equation, writing equations, and then you can find out what force will be required just to start the motion of the block there. Okay, given other variables. So basically you can solve for all these what do you call unknown variables R1, R2, R3 and F. So you can always solve for them. But then one more thing which is very interesting is, what happens if we remove the force F now? Will the block fall down by just moving this wedge rightwards? So that is the question which is termed as I think there is something wrong here. This should be phi, isn't it? Let me erase this. This is this R1 phi, isn't it? This is phi. Yeah, and that R2 is alpha plus phi. Fine. Yeah, what I was telling is, so that is termed as something called self-locking or not. That means if this block doesn't come down when we remove this force F. See, we were applying a force to move it up, but now we have removed the force, but still this thing is not coming down. It is just staying like that. So it is locked. So it is called self-locked system. So now what are the conditions of this self-locked system? That is a very interesting topic which should be discussed, and to discuss that we should in fact draw the free body diagram in two conditions. What are those conditions? Let's go here. See, when we said that it is on the verge of slipping, at both these places, see this phi and this phi. Okay, so the reaction forces were completely at the maximum limit. They were not about to move beyond that phi, because all the surfaces were just about to slip. Otherwise things will not start moving, isn't it? So that's the condition of slippage. But if we come to the case that something is locked, then things can be locked if a single surface is locked, right? That means there can be two cases. For example, first case is the upper surface is on the verge of slippage, but the bottom surface is stuck. Then also it won't move. Similarly, the other case is the bottom surface or the pair of surfaces, this bottom pair of surfaces, they are on the verge of slipping, but the upper pair of surfaces, that is this, that is stuck. In either of these two cases, the whole system will not move. Now let's see, from these two cases, can we have a condition under which the system of wedges will be self-locked, because this is very important. If this condition doesn't apply in a particular case, even in a screw case, I mean, just imagine, right? You have done so much of work to move it up, and then you just left the force, and after you come back from lunch, then this block is completely, again it has come down, and then this block has been shifted. It's bad. In fact, practically it is not required. I mean, it's not desirable. So that means we need to see under what conditions it should be self-locked, because see, intuitively you can think that, right, if I increase the angle alpha, there will be a greater tendency that it will be pushed sideways. If alpha is small for a given friction, okay, I am considering that the friction value is a constant, and then for that given constant value of friction, if I decrease alpha, there will be less sideward force and then less tendency of being unlocking. Okay, so let's see then what are the condition of locking. Now, when we have removed the force, let's draw the free body diagram of the wedge. Now, case 1, so I will draw case 1 here, in which say this is the wedge, okay, and then I will draw the vertical to the ground, okay, and then I will draw also the perpendicular to this surface. So this angle is anyway alpha. Okay. Now just imagine that and then now there is no sideward force, right? So it will be subjected to only two forces. Now it will become a two force member. Okay, let's try to draw the friction, not the friction, the reaction force which is coming. So the reaction which will come will be say in this direction. So this is R2 which I had drawn, and this so I'll say this angle being phi. Okay, imagine that phi for this case, you can actually draw for the other case. Now let's imagine or assume that the phi is more than alpha. Okay, so that is the case which we are showing. So now it is assumed that this surface, this pair of surfaces, they are on the verge of slipping. So that is why R2 will make an angle phi with the perpendicular to the surface. But then we have discussed that it's a two force member and it is in equilibrium. That means the other reaction has to be collinear with this. There is no way out for that. So in this same direction, same line of action, it will be R1. I should write it here maybe. Sorry, I'll write it here so that I can draw the perpendiculars. Okay, so that's the way it will be, and in fact so this angle will be how much? This is phi minus alpha, isn't it? Phi minus so this angle will be phi minus alpha. Okay, so that will be the condition of equilibrium when these upper surfaces are on the verge of slippage, lower one is stuck. Let's see what happens on the other case, that is the upper surfaces is stuck and the lower surfaces are on the verge of slipping. That means it will just be like this. So reaction R1 will be like this, and this angle now will be phi, and what happens at the top? Again let's see, the force will, let me first draw the force. So this will be exactly opposite and R2, because it is again in balance, with a 2 force condition. There are no third force, and if that is so, then now let me draw the actual vertical here, the ground vertical and the surface perpendicular. Okay. Now then this becomes your, because this is alpha. Now let us say this is alpha and this is phi minus alpha. Okay. So that's the condition when the bottom surfaces are on the verge of slipping and the upper one is stuck. Now let's combine both these pictures. Okay, so that we will get the condition under which this will, the self-locking condition can be seen. Now let's see, we will draw the vertical like that, the ground vertical, and say the, yeah, that should be fine. And then let's see R2, it can vary from what to what. So now in this case it is in this direction with and in this case it is in this direction, sorry. Okay, and what are the angles? Let me see. So this was with respect to, let's say, now I'll draw this one, the surface perpendicular also. Okay, now this is phi R2 in this case, and this is phi minus alpha. Let's say this angle is phi, this angle is phi minus alpha. Is that fine? Then what is the total angle? The total angle, this total angle becomes, say, 2 phi minus alpha. Okay. Now let's come to this side. Now this side, this angle is what? R1. Okay, this is alpha, this is phi, and this side, this was, like that. Now this was R1, so I'll write here R2, say R2 and R2 in different conditions. Okay, you have to understand this middle picture, that it is a superimposition of these two cases, so that we are just trying to see there's the range over which R2 and R1 can move to keep things intact. Okay. Now here this angle is phi. Okay. This this angle is phi, and what about this angle? This angle is phi minus alpha. This is phi minus alpha. So what is the total angle? Again 2 phi minus alpha. Okay. Now that means if we have chosen alphas and phis in such a way that this 2 phi minus alpha is greater than 0, okay, then the R1s and R2s have some space so that they can adjust themselves and the thing, and both of them will be stuck. Okay. And so that has to be carefully understood. Okay. So what I was telling is, now this is the condition, or you can write in this way also, 2 phi is greater than alpha. So if this is the condition, then the wedge is self-locked. That means it's a very subtle thing, so please try to understand what's happening. Now when this thing is positive or greater than 0, physically what it means is you have these angles at some angle R1 can balance itself or position itself so that it can actually balance R2 which is coming from that. Now if this is less than 0, that means you don't have this condition satisfied. See, suppose you are increasing alpha. So this zone is becoming narrower and narrower. This zone also becoming narrower and narrower. And a point comes where you don't have any leeway. Okay, you don't have any space over which R1 and R2 can rotate. Then what happens? Then the balance cannot be sustained and the block will slide down. So this is the condition of self-locking. So with these conditions, so please what you can do is you can also do two things. One is here we have drawn for the case when phi is more than alpha. So you can do one thing, that you can draw the similar pictures when phi is less than alpha, because under that condition also a situation can happen that 2 phi becomes more than alpha. Doesn't require that phi should be more than alpha to have 2 phi being more than alpha. So the other case which I am telling you to draw is the case where phi is less than alpha but still 2 phi is greater than alpha. There the case of locking will happen. That is one. One more point which you can try to convince yourself by drawing free body diagrams, that what will be the force which will be required to move it now. Suppose the system is self-locked. Okay, it is not moving on its own. That means now you have to apply a force in the opposite direction so that it will come down. So what is that force? The pulling force. So that you should, so these two things you should try to do on your own, and it will give you a lot of understanding of these concepts. Okay, see you then in the next segment.